Hi, everyone, and thank you so much for coming to my speaking skills talk. While, as Asha has mentioned, my bread and butter research is in reinforcement learning and dynamics models, I happen through some strange coincidences to discover a very interesting application of old and classic computer vision techniques that have fallen by the wayside. I hope that I can share with you the series of little aha moments that I had as I learned to apply a completely new application of techniques that I thought would never be relevant or perhaps see the light of day again. The work in this talk was done with Professor Ruben Martins and has been submitted to some conferences, but the paper hasn't been published online yet. Now, I'd like to begin by introducing the core problem we are trying to solve. We are trying to do something called two-dimensional bin packing, in which we have a bunch of differently shaped rectangular objects that we wish to pack in as few bins as possible. The objects are all of different sizes, and the bins are all of the same sizes, and the goal is to use as few bins as possible. Rotating objects may or may not be permitted, depending on the exact setting. Additionally, we generally assume that all bins and objects have integer sizes. This is, we can reduce continuous size problems to these quite easily, and some nice properties we get out of making this assumption. So pretty much everyone in the literature assumes that you can treat your bin packing problem as though it has integer sizes everywhere. And our job is, given a bunch of objects and a bin size, to find an optimal packing. Now, optimal packings are strongly NP hard to compute. That means even if you fix the size of the bin and the maximum or minimum size of the objects involved, you can still find it instances that are NP hard to compute. On top of that, the solutions are strongly symmetric. Now, most ways to tackle NP hard problems in practice typically involve some kind of combinatorial optimization techniques, and symmetric solutions tend to make those methods work even more slowly. And so despite all these difficulties, this is an interesting and useful problem to solve because it has many, many industrial applications. So material cutting, for example, for job shop or low volume, high variance manufacturing, as it's called, relies heavily on solving such problems, as does PCB panelization, where if you have a PCB fabrication shop that takes in maybe a dozen different designs and has to make about 10 to 50 pieces of each design, this type of technique will help them greatly, in theory, save on the total number of panels they have to produce. And finally, there is some application to CPU and RAM-aware job scheduling. If you assume that each bin can be any two different resources and the objects cannot be rotated, then this is exactly equal to a scheduling problem that you might wish to solve. And because of its numerous practical applications, there are many close variants of this problem. We are studying the relatively simple variant in which you can pack objects pretty much as you see fit without rotations, but there are variants that permit rotations. There are variants in which you have to respond in an online manner to incoming requests, where you get penalized for a delay between receiving a request and servicing it, and guillotine cutting, where you wish to cut using a guillotine paper cutter, which makes a single cut across the entire width or length of whatever sub-piece you have. And all these variants are studied extensively in the operations research literature, which has come up with a bunch of existing solutions to this. We can broadly categorize it into approximate solutions, which generally have a competitive ratio of about just over 2, meaning that if the optimal solution takes n number of bins, this approximate solution is guaranteed to never do worse than 2n1/8 times n, which is great. A reasonable ratio to achieve for approximation algorithms until you realize that titanium can cost upwards of $6,000 a sheet. And at that point, you're suddenly much more interested in exact solutions that will save you potentially a lot of money in your application. Now, there are two modern exact solutions that rely on combinatorial optimization techniques at their core. The first is combinatorial Bender's decomposition, which uses two different kinds of combinatorial optimization techniques together. And The strength of this combinatorial Bender's decomposition, which we will only briefly be touching on, is that they have found ways to generalize from one infeasible assignment to many other infeasible assignments. This type of decomposition is not uncommon in the theory side of combinatorial optimization techniques. And they found a way to make this practical and a key application in which this is useful. The other technique, the one that we'll be discussing in much more detail today, is called positions and covering, in which a single integer linear program, which I'll explain in just a second, both assigns objects to bins and finds a position within a bin for each object. The strength of this technique is it depends on being able to efficiently break the symmetries in the underlying solution space. We'll be getting into that in a little bit. As a brief aside, I imagine everyone here is familiar with this, but I just like to get everyone caught up. An integer linear program is an optimization problem in which your objective is linear, your constraints are all described as a matrix multiplication and less than equal to a vector, and your decision variables are only integers in our case. There are many other such programs that are similar, but for the sake of this particular presentation, we're only going to focus, we're going to translate our problem into an integer linear program and solve it. In addition to that, this is the so-called canonical form of an integer linear program. And instead of specifying problems directly in this manner, which is rather inconvenient, we, in practice, typically specify them symbolically and use a standard off-the-shelf software package to translate them into this standard form, solve them, and translate them back into a nice symbolic form that we use. And this greatly reduces the complexity of thinking about the problem. As long as we can guarantee that our objective is linear, our constraints are convex, and our decision variables are integers, we don't have to write the problem down in this way. We can write it down in any other way that's perhaps intellectually more manageable, and then rely on some other piece of software to handle the translation for us. Great. So now that we've gotten so far, let me begin by describing how positions and covering works. Positions and covering is a two-stage encoding scheme that constructs an integer linear program to solve the 2D bin packing problem. The idea behind it is that we begin by specifying some key decision variables, and then we transform the decision variables in two different ways in order to specify different key constraints that are necessary for an ILP to accurately specify our problem as an integer linear program. On the left, we start with the key decision variables, which is for each object, what bin it is assigned to, and what the row and column of its top left-hand edge is, corner is. Once we start from that, we wish to actually find these values. So in order to find these values, we translate this key decision variable into first a positions transform, in which a cell has value 1 only if the decision variables say that the object should begin in this position. And we use this to enforce only strictly legal positions, meaning an object cannot exist outside of the bin, cannot have any part of itself land outside any bin. That's the constraint we encode here. And then we again transform this into a coverings by the so-called coverings transformation, where we have a value 1 for each cell occupied by each object. And we use this to enforce a no overlapping constraint, meaning that no two objects can occupy the same cell of the bin. Does this make sense so far? I'll be going into detail in the transformation in just a second. All right, great, thank you. So to drill down in a little bit of detail, the positions transform is very simple. It just says that the variable at position PQIJ is 1, if and only if the object P is in bin Q, and the top left-hand corner is at position I, j. So for a bunch of possible object positions, I've shown you what the positions matrix would look like. Now, bear in mind that we are not constructing a single matrix. We're not constructing a matrix based on a single assignment. We are instead creating one variable for each cell of this matrix and building in constraints so that the value is 1 if the key decision variables say that the object is at this position. So we have one variable for each cell in the positions matrix, and additionally one constraint to show that, to enforce this property. Now that we have this, we use the positions matrix to enforce that every object cannot exist outside of the bin, and also to build the coverings matrix. The coverings matrix simply says that the variable at pqij is 1 if and only if the object p at bin q overlaps with position I and j, meaning if any part of the object occupies cell I and j. This is, again, specified using a bunch of constraints. And once we have this matrix, we can very quickly say that we don't wish to have any two objects overlapping by simply saying that for any position, for every object P in bin Q at position I and J, there can be only one object occupying that position. Does this make sense so far? All right, fantastic. So at this point, I wish to observe that there are a lot of constraints required to express this. There are a lot of constraints required to specify what we're calling the overlap matrix. And this leads to, frankly, a rather lot of constraints required to specify the positions and covering transformation collectively. In the worst case, we need as many constraints as the number of objects times the number of bins times the size of each bin squared. And this is rather painful. Like, no one wants to see a polynomial blow up in their convex in their combinatorial optimization technique. It's already bad enough as it is. Let's not make it worse if we can. So I'm about to present our method in which we significantly reduce the number of constraints and the complexity, and we're able to show that this translates into speed up in the real world. But first, a brief aside to link this to computer vision and how this translates in, how this maps to the Hough transform from classic computer vision. Now, I'm not sure, this method might be familiar. If you are over the age of about 30, you might have encountered this at some point. But this was innovative and patented in 1962 by a gentleman named Paul Hough. And before this happened, automated part inspections were done used by having an artist paint a sheet of acetate with the negative of the object you wish to track, and using mechanical means to align objects and take a flash and measure the amount of light that is not, that passes through where light shouldn't be, or vice versa. And these old analog techniques were the exciting methods of the day in the 1940s and 50s. In fact, I think Carnegie Mellon still has one such optical comparator machine in Hammerschlag Hall, but I think the person who knows how to operate that machine recently retired, and so the machine exists, but the knowledge has been lost, unfortunately. Paul Hough in 1962 invented something called the Hough transform, in which he maps each XY point on a source image to a gradient intercept point in parameter space from a line, meaning each point on each line is translated onto a series of possible points corresponding to the line that could have generated that point. We call this type of technique a parameter space transform today, and it's mostly fallen by the wayside, limited only to some applications in fitting parametric distributions, and even then, not a very common way of doing that. This venerable classic technique from, I think, even before my parents' time, is exactly what the positions technique, the position stage is trying to do, transforming it from one encoding scheme into a parameter space that more closely matches the natural intuition or the physical meaning of the underlying problem. Now, quickly, now that we've briefly skipped off our side, we'll come back to the Hough and Cover, which is our contribution. Now, our contribution is in much more efficiently performing the coverings transformation by representing the coverings matrix as the cumulative sum of a delta matrix pre-image. I'll explain this in just a second. But the purpose of doing this is that we can reorder operations and greatly reduce the total number of constraints that we need to represent the coverings matrix from the positions matrix. Now, the idea of a delta matrix itself comes from a different part of classic computer vision. And it's it's a common operation afforded in libraries like NumPy and R. The notion of a cumulative sum is that for each cell, the cumulative sum at that cell is equal to the sum of all values to the left, above, or both of that cell. Or this cell stores the result of this sum over here. And this looks at first like a relatively complicated operation to perform, but there's a linear time algorithm to perform this that uses, that if you perform the sum in row major order, uses the property that the value at this cell is equal to this value plus this value less this value. And this fantastic construction allows you to perform this computation in row major order in a constant number of operations per cell that you wish to fill. The idea for this was popularized in the 2001 Viola-Jones face detection paper. Before neural networks were a thing, face detection was done using handcrafted Haar-like features, these rectangular objects over here, which were placed in a sliding window fashion over faces. And a tree of these objects was learned in order to more effectively identify faces. The trick to compute a Haar-like feature value or the feature response is the sum of everything in the white region less the sum of everything in the black regions. And now computing this in a naive fashion is very expensive. So instead, what Viola and Jones did back in the old Mitsubishi Electric Research Lab and Compaq Research Labs, stuff that was long gone before my time, unfortunately, is they pre-computed the cumulative sum across the entire source image. And that way they could compute the value, the filter response of at any one position in a constant number of operations. If I remember correctly from the paper, they could compute any one of the 6 filters they wished in at most 12 addition or subtraction operations, which is mind-blowingly fast. And on 2001 hardware, they were able to get face detection at something like 26 or 27 frames per second back on 2001 hardware. Again, impressive. This technique, they themselves attribute to a classic computer graphics technique invented 9 years before Doom was a thing. So yeah, now, but using this classic technique, we are able to rewrite the generation of the coverings matrix as first a delta and then a coverings, and then from there the overlap. And so far we haven't saved anything, but this type of rewriting allows us to reorder the operations. And when we actually reorder the operations, we notice that we can save quite a lot of constraints. So once again, if you were to think of the way we've talked about it so far, we'd start from the delta matrix. We'd first perform the cumulative sum operation to get a coverings matrix, and then take the sum over all objects to get the overlap matrix. Instead, we can switch the order of these two operations and go from a delta matrix to what we're calling a sum delta matrix, and then the cumulative operation to get the overlap matrix. And by doing so, we avoid having to specify one constraint for each potential from and to cell in the coverings matrix. Now, let me present to you what this looks like graphically, as I hope to give you some intuition on this. So if we have these 5 objects scattered in this packing form, these are the individual delta matrix of each object. We're hiding all the values that are trivially 0 for simplicity. And the cumulative sum of each individual object will give you the coverings matrix for that object. Does this make sense so far? I sense I might have lost you. So if you have a question now, I'll be happy to answer.
I think this is a crucial part. Can you elaborate a bit more on this slide?
Of course, I'm happy to. So notice that if we go back to positions and covering, and positions and covering transform works is you go from positions to covering, and then from there to overlap. And that's how you specify you do not wish to have 2 objects occupying the same space. Great. Hough and cover, instead of going from positions to covering to overlap, we go from positions to delta to coverings to overlap. And by doing so, we can skip having to specify the coverings matrix, instead going delta to sum delta to overlap. And for the rest of this talk, I will be showing you why this reordering is possible and how doing this reordering allows us to save a lot of constraints. The intuition behind why this method works is what I'm trying to present over here. The intuition is that if you take these individual delta matrices, you can take the sum of these matrices to get the sum delta matrix and then perform the cumulative sum over that. You can do either first sum, then cumulative sum, or first cumulative sum and then sum. And your output at the end of both of these will be the same. That's the intuition I'm going to present over here. If you have these individual delta matrices, you can just take the sum over all these delta matrices. And this, the cumulative sum of this will be exactly equal to the overlap matrix. If you wish to verify this numerically, it's possible, but I'll present you an intuition for why this is true in just a moment. The key point I wish to note over here is that going from delta to coverings matrix requires specifying one constraint for every cell from every position, which is where we get the quadratic blow up in our constraints. Instead, the sum delta matrix requires a constant number of constraints to specify. Oh, my mistake. The delta matrix requires a constant number of constraints to specify. For each possible position, you need exactly 4 constraints to specify 1, 2, 3, and 4 values in the individual delta matrix. And then you need only a number of constraints equal to the number of these matrices you're summing up to get you to the sum delta matrix for each cell.
Maybe can you give already kind of some highlight what the requirement is on this sum delta matrix, how to see that there's no overlap?
Great. So the way you see there is no overlap from the sum delta matrix is you simply take the cumulative sum of this. We perform this operation that we are talking about using this mechanism to evaluate it. And that way we can recover exactly the overlap matrix. And then we just say we want there to be at most one object per cell of the overlap matrix. Another way to think about it is that as we perform the cumulative sum operation, we can just say that we never wish the current running value of the sum of our, as we are scanning through in row major order, we never wish the current value of it to exceed 1. And that is exactly the same as specifying it this way.
Okay, thank you.
Excellent. And the benefit of reordering these operations using this cumulative sum operation that you've stolen from classic computer vision is that we lose the quadratic term in our in the number of constraints we need to specify this. Instead of taking a potentially quadratic number of constraints to specify the coverage matrix from the position matrix, we take a linear in the number of cells, a constant in the number of cells, followed by a linear in the number of objects specification. And Bob's your uncle. This is how we greatly save on the number of operations we need. Now, does this make sense so far? From this point onwards, I'm going to be explaining why it's possible to reorder these operations. There is a very cool underlying concept, again stolen from a little bit more modern computer vision, that lets us prove almost trivially why it's possible to rewrite these operations. Okay, great. So the key property I wish to point out is that both the sum and the cumulative sum operations can be written as convolutions. And convolutions, all linear operations have the property that they are distributive and associative. Convolutions in particular are also commutative. And the commutative property means that we can reorder these operations. Now, there is a caveat, as always. It depends very much on the exact boundary conditions. And in the paper we've written, we give that a bit more detailed treatment to show that we're not violating any of those boundary conditions. But it is possible to reorder convolutions in virtually limitless manner. And not just that, but these convolutions and properties of these convolutions are used everywhere. Even the construction of the 2-dimensional delta matrix, it seems arbitrary at first, but I wish to point out that the delta matrix itself is the cross product of 2 one-dimensional delta matrices. And the cumulative sum of a one-dimensional operation is, in this way, it generalizes to the 2-dimensional and even higher dimensional cases using this mechanism. In modern computer vision, convolution properties, not this particular property, but other such properties are routinely exploited in, say, transformers, MLP mixers, architectures, ResNets, etc. And they form and individual properties of convolutions form the backbone of many such techniques. In this case, the commutativity of convolutions is what we are exploiting to give us this particular result. It's not just this one stage or two stages that are convolutions, but all stages. Starting from a positions matrix can be written down as convolutions. So this is the perhaps the third link to computer vision that we have in our talk. And from this point onwards, I'll just be talking about the results and some interesting points that we've observed. So of course, naturally, as with any bit of research, we have a fantastic implementation written in the industry standard language of Julia. We use Gurobi as the underlying solver. We implement both techniques with pre-processing, which I'm going to omit for the sake of brevity. Pre-processing is itself probably a couple of hours worth of content to cover. And we use an objective function to minimize the number of bins. We have some heuristics to bound the lower and upper number of bins, and we add an objective function to use exactly as few bins as possible. And we observe in this chart, charting the number of constraints in a problem with respect to the number of an experiment as sorted by the number of constraints in Hough and Cover. We observe that Hough and Cover consistently uses fewer constraints. However, the gap that we observe is bimodal. It's almost like there are two distinct categories of problems in which Hough and Cover performs, in which positions covering takes a different number of overhead, a different size of overhead, depending on the exact problem. This is explained by the fact that Hough and Cover uses a constant number, uses a number of constraints that is independent of the size of each object. Recall that in our delta matrix formulation, we use exactly 4 constraints, one for each corner of the object that we are trying to specify. In positions and covering, the coverings matrix uses 1 constraint for each cell inside each object. This means that the number of constraints used for positions and covering depends on the size of each object in the problem, and the number of constraints used is independent of that in Hough and Cover. We traced this problem down to the particular standard data set that we are trying to solve using our these two methods. It's called the Unibo data set, named after the Unibo Operations Research Group in out of Italy. It's a very old data set that for even as few as 80 objects still has some unsolved problems. And in the creation of that data set, the problem sets that they drew from were 2 distinct older problem sets that they cleaned up and presented in a coherent manner. And these 2 different problem sets have one of these initial problem sets uses a lot of small objects and one uses a lot of large objects. And this is why we get this interesting bimodal gap in the number of constraints that we actually develop. And now finally, once we have this implementation, we actually use it to solve a selected subset of the standard Unibo data set I just mentioned. And we plot a comb plot showing the speed up ratio that Hough and Cover achieves over positions and covering. Notice that this comb plot, the x-axis reflects the amount of time taken by Hough and Cover, and all ratios where Hough and Cover does better than 5:1 over positions and covering are truncated in order to save computation time. You'll see that as hollow teeth versus the solid filled-in teeth. So we notice that we tend to do better, and the margin qualitatively, I like to observe that we do better more as the problems get longer to solve. Now, there are, as always, some things I should mention, in particular that we did these evaluations with a small suite of standard pre-processing applied to both. Both methods received exactly the same pre-processing techniques using the same solver to make as fair a comparison as possible. In the actual state-of-the-art implementation, there are many, many more pre-processing steps involved, including pre-packing and heuristic solutions that, for the sake of simplicity and brevity, we have not mentioned over here. Once again, and this concludes the presentation. Thank you so much for your time. I'm more than happy to take any questions about this technique.